So, welcome student. Welcome to today's class. So, this is MA415 Algebra. Okay, and this is the lecture number 24, I guess. Yes. Okay, so we have discussed about rings and ideals, and today we will learn something called isomorphism theorems. Okay, so that the similar theorems we already learned in group theory, and we have the ring theory analog of those theorems. Okay, so let me start with the theorem. So maybe the first isomorphism theorem. Isomorphism theorem for ring. Okay, so now we are doing ring theory. Okay, so what does it say? Suppose you have a rings R1 and R2, and suppose you have a homomorphism phi, then this theorem tells you that we know that kernel of the homomorphism is an ideal, so you can talk about R1 mod the kernel of phi, and this is as a ring. So as a ring, this is isomorphic to image of this phi of R1. So phi of R1 is a subring of R2, right? So it's as rings, they are isomorphic as rings. Okay, this is that first isomorphism theorem tells us. Okay, so and the proof, whatever we discussed last time, so we can discuss similar kind of proof here also. So how do I prove this? So proof so let me write down that kernel has a name. Say I is the kernel of phi. Okay, and I need to define first of all a map from then R mod I to this phi of R1, phi of R1, right? This is the map I need to define. So how do I define a map? So let me define a map. So define this psi is a map from R mod I to phi of R1. You recall phi is a map from R1 to R2, right? Now, so phi of, so what are the elements of R mod I? This is of the form R plus I, right? And do you have any image like what are the image? This is the natural question. So if we map this thing phi of R plus this, what will be the image of this? Can you guess? You have an element. What will natural element here? Natural element here will be phi of R. This is the natural element, right? Because phi is a map from, it's given that phi is a map from R1 to R2. It's a ring homomorphism. This is given. Homomorphism. Okay. Yeah, maybe I should say this is ring homomorphism. Okay. I said already, but let me write down. Okay. So now if I define the map psi from R mod the kernel to image of the phi, then this will be the natural map, right? The question is that whether this map satisfies the property of homomorphism. Also bijective or not. Okay, so how do you prove this kind of thing? So so for homomorphism, what I need to prove? I need to check that suppose you have two elements R1 R2, right? So psi of R1 plus I, okay, and so this is one element, and another element is, so this is ring homomorphism we need to check, right? So we need to check two property. First this, now what will be this? This will be nothing but psi of R1 plus R2 plus I, right? Addition of the elements, and then by property this is phi of R1 plus R2, right? But I know that phi is a ring homomorphism, so this will be phi of R1 plus phi of R2, right? But what is phi of R1? Phi of R1 is nothing but psi of R1 plus I plus psi of R2 plus I. So the first property of homomorphism satisfied. Okay. Now I need to check it for multiplication, and similarly you can do it similarly. What you can say? You can write down phi of R1 plus I into R2 plus I, right? And this you can write down by this multiplication of quotient ring R1 R2 plus I, right? But again this is nothing but, by definition of psi, it is nothing but phi of R1 R2. But again we know that phi is a homomorphism, ring homomorphism, so this is nothing but phi of R1 into phi of R2. Okay, and thus this is nothing but psi of R1 plus I into psi of R2 plus I. Done. So it's natural to check that it satisfies both the property. Okay. Yes. So now yeah. So both the properties satisfied. Now we need to check that this is bijective map. Now to check bijective map, what do you need to check? So yeah. So obviously, see, there are two ways you can do it. First of all, you know that this I is they have a group structure, right? So this one is it has a group structure also, a quotient group. Now we know that if you have a quotient group, and if you go homomorphism, then this equal to this isomorphic to this as a group. And in addition, you need to you just prove that it is also satisfies the ring homo property, so this is a ring. So you can say like that, or you can directly prove this is one and onto map. That also possible. So to prove one and onto-ness, what you need to do? You need to just start with that. Suppose so let psi of R1 plus I equal to psi of. So I am going to check injectivity property. So let me assume that these two image are same. We will say that two image also same. So what does that mean? That means, so this is yeah. So what does that mean? That means this is phi of R1 equal to phi of R2, right? By definition. Now what does that mean? That means, see, this is a ring homomorphism, right? So this is phi of R1 and phi of R2 inverse. This is equal to identity, right? And that is nothing but, okay, so I am assuming throughout the lectures that R is a unital ring. Okay, so ring with identity, ring with identity. Okay, so yeah, so and then this is nothing but phi of R1 into phi of R2 inverse, which is equal to identity, and that implies that again the homomorphism property tells you that this is R1 R2 inverse equal to identity, right? Or rather, no, I will show that the kernel. Okay, so rather it is better to show is using the kernel property. Yes. Mm, so then yes, 1 minute. Yeah. So rather than this, I don't need actually identity. Yeah, I don't need identity. I think I can easily prove without identity. So let me prove that without identity. Mm, yes. I don't need this property actually. Here I can easily prove it. Okay, so this I can write down phi of R1 minus R2 equal to 0. Yes, and that will gives me phi of R1 minus R2 that equal to 0, right? So what does that mean? That means R1 minus R2, this is an element of the kernel of phi. Yeah, this is which is equal to I. Okay, so yeah, this is much easier. So this difference of these two elements inside this, and what does that mean? So that means the you remember that what is R1 plus I? This is the cosets of um, R1, right? So that means this R1 and R2 are equivalent, right? The way we define it. So their cosets are same. So R1 plus I equal to R2 plus I. The cosets are same. Yeah, so actually I don't need identity property here. I can easily prove. Okay, so this shows that psi is 1 mapping. Okay, and surjectivity is also by definition. You can see this, so it's by definition, right? So let you choose any element. I mean, X belongs to this image of this, right? Then there exists some R in R1 such that this X equal to phi of R, right? Because this is inside the image of this thing, right? So what does that mean? That means X equal to phi of R, but what is phi of R? This is psi of R plus I. So given an element inside this range, you will have you have a pre-image here, right? This is almost by definition. So size 1 2. Thus psi is a ring um, ring isomorphism. Clear? Yes. Done. So this proves that whenever you have a ring homomorphism from a ring to another ring, then the quotient ring formed by the kernel is isomorphic to the image of that homomorphism. Okay. Yes. So now let us discuss the example what I discussed many times, that you have this polynomial ring, and then you can have Z, and your natural homomorphism cross that. So phi of f of x that equals to f of 0. Remember, so this is a constant term. So in polynomial you are sending the constant term. Okay, and this was obviously homomorphism. You can easily prove that phi of f1x plus f2 of x, this is nothing but phi of f1 plus f2 of x, which is nothing but f1 0 plus f2 of 0, right, which is nothing but phi of f1x plus phi of f2 of x, right, and similarly phi of f1x into f2x. Okay, so just see define. Yes, so now you are sending this phi of f1 f2, think about f1 f2 of 0, which is nothing but here I write down f1 0 into f2 0, and thus you have phi of f1x into phi of f2x. So this is a leading homomorphism. This is clear, and you can find out what is the kernel. So what is the kernel of this homomorphism? Kernel of phi. So this is nothing but all those fx inside the integer polynomial ring such that f of 0 equal constant term equal to 0, right? Because 0 is the 0 element here inside ring, so this is 0. Now what does that mean? That means that so if of x equal to 0 means what? That means the polynomial is divisible by, okay, so the polynomial start with x, right? X term minimum. It can be x square or other thing also. So what does that mean? That means all those fx belongs to zx such that this x, so fx is of the form x times some gx, right? Minimum x is there for some gx belong to zx, right? But what is this? This is nothing but actually the ideal generated by x. This is called the ideal generated by x, right? Everything multiple of x, right? So this is the actual kernel of this homomorphism, and hence you can talk about what is the range? What is phi of zx? Any idea? Now you see that this is nothing but the full integer, right? So this phi is onto, as phi is onto, right? Phi is onto, can you prove it? Homework. Nothing to prove actually. So given an integer z, that is that constant polynomial, right? The p image is there always. So phi is onto. Okay. So so what does that mean? Then first Isomorphism theorem tells us that this zx modulo by this ideal generated by this is isomorphic to z. Okay, so then this is one example. There are plenty of such examples. Maybe we can do one by one. Maybe I can give you one more example for the say non-commutative ring. See, this is commutative ring, so many things is easier. So maybe example 2. So let me take my ring R, which is some okay, so maybe this is R dash, let me write down. and this is some n cross n matrix over ring R. Okay, so you choose a ring, or yeah, you choose any ring, not a field, and then you define that n cross n matrices over the ring R. What the ring R means what? That means that the entries are element of the ring R. Okay. So this is obviously not contradicting because the matrix multiplication is not commutative, right? Now, let me find out one. Let me find out one examples. In that case, I can give you an example where um, the ideal of this. So let say J be an ideal of R. Okay. So if you have ideal of R, then you check that if you define by this M n J. So this is what? This is all those matrices inside M n R such that the entries are from J. Okay. So inside MNR you choose all those matrices whose entries, like so if you write down A equal to Aij, this Aij is an element of J. J is the ideal of so now can you say that this is an ideal? So actually this is an ideal. So this form this forms an ideal of MNJ as MNR. Okay, so MNJ is an ideal of MNR. This is simple proof property. So maybe I can give you some hints. So how to prove this is an ideal? So you multiply, you choose an element of MNJ, and if you choose an element of MNR, and then when you take this multiplication, matrix multiplication, then what happens? Then element of J's are multiplying by element of R, right? But J is an ideal of R, so whenever you multiply by element of J and R, that will be element of J itself. So this is the proof actually. This is an ideal of R. So you can define and then this homomorphism and everything. Okay. So what is that map? So 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 question is that uh, can you can you find out this ideal? This is an ideal of this, right? Now can you find out a two rings such that this becomes a kernel of some of them, right? So this is also you can prove that uh, and like ideals. So kernel are the ideals, and you also prove that every ideals of a ring becomes sitting inside the kernel of some homomorphism, right? That also you can prove. For example, given a ring R and I be let be a ring and I be an ideal, then you can always prove that I is kernel of something. So you define the map from R to R mod I, the natural map, and what is natural map? Phi goes to I goes to R plus I, and you see that this kernel of this phi is nothing but I. So an ideal is always an um, um, always and kernel of some homomorphism. Converse is also true. If you have homomorphism, then kernel is always an ideal, right? Now question is that whatever the example I gave you here, one nice ideal. Can you find out a ring homomorphism of two rings such that this is sitting as an ideal? And this is simple. You can also check it. Now I am writing this map from MNR to MNR mod J. Okay. See, J is an ideal of R, so R mod J is again a ring, right? So you can talk about the ring, and then you define the map phi. Now what is the phi? So this is simple. You just take a matrix A here, which is nothing but Aij, and under phi, what is map? In map, something say A bar. What is A bar? A bar is Ij bar, where Ij bar is nothing but Ij mod J. Okay, so if you take the modulo J, then then it becomes the element of Ij bar, right? So see, understood. So element of R mod J's are nothing but modulo element, right? Something modulo J. So you can take Ij inside to this. Now if this is the ring homomorphism, this is natural ring homomorphism, and now you find out what is the kernel. The kernel of this is nothing but exactly what I just discussed. This is nothing but Mnj. Okay, you can do it as homework. Okay, so obviously, and also you can prove that this is an onto map. So this is an onto map actually, and hence you can say that MNR mod MNJ is isomorphic to MNR mod J. Clear? Okay, so this is one observation of ring homomorphism. Now let us define other homomorphism. So second isomorphism theorem, isomorphism theorem for ring. I am not writing for ring again and again, right? So suppose now we have ring R, and you have so now I am assuming two things. One, you have an ideal, another is a subring. So suppose you have a subring. So this is the ring given. Now let S be a subring of R, and I be an ideal of R. This is given to me, and then I can define a nice structure S plus I. So what is my S plus I? This is of the element of the form X belongs to S. Okay, so sorry, I need to write down what are those things first. So this is X plus Y of this form, and this is the first element. X is the element of S, Y is an element of I. Okay, so consider these kind of structures. So this is actually subring of R. Okay, so this become a subring of is a subring of R. So this is first property, and second, not only that. So once this subring of R, then obviously I is an ideal of this. Okay, so second is what? Second is that, or rather, Roman, yeah. This second isomorphism theorem. And number two is what? So you take this intersection, this is intersection I, Okay, so S intersection I is non-empty, right? Zero is always there. So this is actually a subset of S, right? This is inside S. But it is not only sitting inside S, this is something more. What more? So this is an ideal of S actually. See, S intersection R actually become ideal of S, and so there are two things. One is that S plus I is a subring, and you know that I is an ideal of R, so I is also ideal of S mod I. So you can talk about the quotient being S mod I in the one hand. On the other hand, you can talk about, because S plus I is ideal of S, so you can talk about this structure also, S intersection I, right? So there are two structures together, and the question is that what is the relationship between these two structures? And this second assumption tells you that these two are isomorphic as rings. Okay, so they are isomorphic as rings. And this is amazing theorem, right? So if you start with a ideal and one subring, then you define a structure S plus I that becomes subring first of all, and hence naturally I is sitting inside the subring, right? Because S plus I is bigger than containing I. Okay, so let me give a proof for this. So for the put of for I, so you see that first of all I is sitting inside S plus I, right? Because okay, so this is what this is X belong to S. Sorry, again X plus Y such that X belongs to S and Y belongs to I, right? So I need to show that this is subring. So to show something subring, what I need to show? I need to show that this is if two elements are there, A, B, A minus B, right? So let me write down two elements. So suppose x1 plus y1 and x2 plus y2. This is an element of S plus I. Like xi is an element of S, yi is an element of I. So then I need to check that then the x1 plus i1 minus x2 plus i2 is element of the same structure or not, but this is nothing but x1 minus x2 plus y1 minus y2, right? But again, you see this is an element of S because S is a subring, and this is an element of I because I is ideal, is also subring, right? So this is element of S plus I. Okay, and then the product, for product what I need to check? So for product I need to check that x1 plus y1 into x2 plus y2, right? Now if you take product, what will happen? So x1 x2 plus x1 y2. So I don't know about quantitativity, so I need to write down the full thing, y1 y2, right? Now you see that this y1 this is the element of I because y2 y1 are element of C, as y1 y2 element of the ideal, then what happens? Then this whole thing is element of ideal, right? So x1 y2 plus y1 x2 plus x1 y2, these are element of the ideal R. Okay, and then what you left? So you have element of S. This is element of S because it's subring. So this is an element of so this become an element of S plus I. Okay, so thus oh my god, S plus I is a subring of R. Okay, and also I is the ideal of S plus I, right? So you can talk about the quotient ring S plus I. So that exists, right? See, I is the ideal inside R, the full ring. So it will be inside, ideal inside any subring of R, right? So one part is obvious is that now for second part, we need to check that this A's intersection. So A's intersection I is always a subset of S, right? This is there is not a problem. Now I need to check that this is the ideal of S. So how do you check this ideal of S? So first of all, let me check this kind of subring. So again, so let you choose two elements, say x, y, element of S intersection I. Okay. So what does that mean? So both x, y belongs to S, x, y belongs to I, right? So this implies x minus y is also element of S intersection I, right? And x, y is an also element of S intersection I. So this is okay. This is obvious, right? Now we need to check that if we take an element from its intersection I and something from outside that, then it will be absorbed, right? So let me write down, let small s belongs to capital S and small x is an element of S intersection I. Then what we need to check? We need to check is that S time x element of this, but x time is obviously belongs to I, as I is an ideal, right? Also S time x is element of S, as S is a subring. Sorry, yeah, that doesn't matter. Okay. Yeah, so this is an element of this is an element of subring. So closed under this, right? So you choose element of S, this element of S, so product will be element of S, right? It's a subring of I. Okay. So this is thus Sx is element of S intersection I, and similarly x time S is also an element of S intersection I, right? So what does that mean? That means if you choose one element from S intersection I, one from S, then this element absorbed, right? So S intersection I is an ideal. So thus S intersection I is an ideal of S. Okay, clear. Now we need to prove that this S plus this modulo I, this isomorphic to is not S intersection I. That we need to prove, right? This is our goal. Now how do you prove this kind of thing? So I will use the help of first Isomorphism theorem. So let me first start with this. So consider map, say phi, that is map from S plus I to S mod is I, right? So what is the map? So you're sending element, say x plus y, to where? You're sending somewhere here. This is, and what are the element of this? These are cosets, right? So this is x plus S intersection I. Okay, so this is the natural map. Clear? So you take an element and you send it to this. See, anyway, y is an element of S intersection I, so it doesn't matter. Yeah, this is okay. X may not be element of S intersection I. So we will say that what case it is element of this. So now you have to check this is a ring homomorphism first. Okay, if we check this is a subject ring homomorphism, then we can talk about what is the kernel. So let me find out. So to check ring homomorphism what I need to check this so you choose two elements, say phi of say x1 plus y1 and x2 plus y2. Okay, now and then we know that this is nothing but x1 plus x2 plus y1 plus y2, right? Now what are these two elements? So by definition this is nothing but okay, this is nothing but x1 plus x2, the cossets of this, right, with respect to this idea, right? But we know that this is nothing but x1 S intersection I plus x2 of S intersection I. Okay, and thus it is nothing but is equal to phi of x1 plus y1 plus phi of x2 plus y2. Yeah, so this is simple, right? Similarly, the product also, that x1 plus 1 into x2 plus y2, and then again you just check it that this is element of x1 x2 and plus something element of I, right, some y dash, because when you multiply then it's I get absorbed, right? So this becomes x1 x2 plus S intersection I, and hence x1 plus S intersection I into x2 of S intersection I, and done. So this implies phi of S1 sorry x1 plus y1 into phi of x2 plus y2, right? So homomorphism property is okay, and the undoness is also obviously by definition actually. So yeah, because if we choose, so for any x belongs to S mod this, so x is always element of x is also element of x plus I, right? Because 0 is inside the ideal, right? Because x equal to x plus 0 equal to x, right? And what does that mean? That means that phi of this x is so this is a so you take phi of x, so that will be mapping to x. Yeah, so I think x, I should say that x bar. So x bar is element of this, means this is element of x plus x of this form, right? So phi of x equal to x plus s intersection I. So phi is on to, this is simple, phi is on to map. Okay, now does this prove our goal? No, actually. The same question I asked when I did in group theory. I need to check that this, the way I define the map, it is actually well defined. I am sending some set kind of thing. No, this is set theory kind of thing. So I need to check this well-definedness property. Yeah, so how do you check these maps well-defined or not? The process, similarly, whatever we have done in group theory, you can do it, because the rings are always the group with respect to addition, right? First of all, so the well-defined property actually coming from this group theory part. You can check it. So okay, so this we need to also assume well define property of phi. Okay, so after doing all those things, then this is done. Then you just find out what is the kernel. So what is the kernel of phi? So kernel of phi is an element. All the see, I'm sending map from here to here, right? So you choose all the elements which is image is identity. What is identity here? Identity nothing but S intersection I, right? So all those x plus y belongs to S plus I such that the image is identity. So what is the image of this? Image means x plus S intersection I is nothing but identity is same, right? Is identity there. But what does that mean? That means all the elements S plus I, and so this property tells you that x is an element of S intersection I. Clear? So you already know that is what does that mean? That means is an element of I, but y is also an element of I. So x plus y is an element of I, right? So this is what this is. Nothing but you are choosing all the element of I. Your x is an element of I, y is an element of I, so addition is also an element of I. Okay. So you are taking actually the elements of I, right? You can say that this is a subset of I, but converse is always true, right? If you choose an element of I, this is always inside the kernel, because the element of I mapped that thing, right? So this is actually equal. And hence you can use the first isomorphism theorem for a ring, and that will give you x this mod I, which is isomorphic to S modulo S intersection I as rings. So they are intrinsically isomorphics. Okay. So this is the second isomorphism theorem, and the third one is simple. So the proof is simple. So should I give a proof or I don't know? So let's see. The third isomorphism theorem for rings, and what is that? So that tells you that suppose we have two ideals now, I intersect a subset of these are two ideals of R. Okay. So what does that mean? That means I is also ideal of J, right? So then you can talk about first of all you can talk about okay, so let me write down R mod say I on the one hand, and then you can talk about J mod I. So J mod I is the inside R. Okay. You see, J mod I is what? J mod I is an ideal of R mod I. Because whenever you choose an ideal I of R, then you go modulo that becomes an ideal of this, right? So you can ask if it's the ideal, then what about the quotient ring? So what about this J mod I, and it is actually isomorphic to R mod J. This is actually a third isomorphism theorem, and proof is similar again. The way we use group theoretical proof, similar thing. I just give you a hint. So proof. So you need to find out a map from this to this such that the kernel is this, right? So you define a map, say phi, say from R mod I to R mod J by the natural one, so phi of R plus I up to R plus J. Okay, now check that phi is well defined first, and a ring homomorphism, or rather you can say ring onto homomorphism, actually ring homomorphism you say onto, I will write down onto ring homomorphism, right? You can say that this is onto map. Okay, and this is the same thing the way we proved several times. Now what is the kernel of that thing? So let me find out the kernel. So kernel of this phi is element of R plus I. These are element of R mod I, right? Element of R mod I such that the image is, which is R mod J, which is nothing but the identity. So what is the identity of R mod J? This is nothing but J. So what does that mean? That means all those R plus I belongs to R mod I such that R belongs to J. See, R element of J, so this is nothing but R plus J, right? Sorry, J plus I. So what? Here, I mean to say that R the elements of J. So what does that mean? That means J mod I, right? These elements are element of J, right? So these are actually of the form J plus I such that R belongs to J. This is the kernel actually. So you can again use that first isomorphism theorem. You can tell that this quotient is actually isomorphic to R mod J. Okay, so this is obvious. Now I will talk about the correspondence theorems for rings. Okay, so for groups also we will talk about the same thing we will talk about here also. Correspondence theorems for theorem for rings. So what does that tell you? Suppose you have two sets. One set is so you have R and an ideal I. Okay, so in one set you are taking the ideals of R mod I. Okay, so these ideals of R mod I, and another set you have ideals of R containing I. And correspondence theorem tells you that there is a one-to-one bijecting map. So there is a bijection between these two sets. So what does that mean? That means that if you choose an ideal of R mod I, then you choose an ideal, this is of R such that this, then you send this ideal to J mod I. We just prove that J mod I is ideal of this R mod I, right? And conversely, if you choose anything, then you choose that full preimage of that thing. That will be an element containing I. So this is a bijective map. Okay, so maybe I will stop here, or maybe I can. Okay, maybe I should stop here. So. Okay, or maybe let me just define two more ideals. One is sum of ideals, and that is product of ideals. Then I will finish it. Okay. So definitions. So suppose we have, so let I and j be two ideals of varying R, then you can decline the sum of the ideals I1 plus j. This is obvious. So this is what you do. You take an element from I and element from j, and you see that x belongs to I, y belongs to j, and this is an ideal of R. You check it. So this is naturally okay. And the product is what? So product you cannot define like that. So for product you need the finite sum of product. So this is, you take sum of xi yi, and your I is from something, say 1 to some n, for some n. So this is not fixed. So some, we will write down the star. So finite sum. So sum. So this xi is an element of I, and yi an element of j. Okay, so you choose some element of xi and yi and take the finite sums. Okay, then also this forms an ideal. This forms an ideal. So this is, you can easily find out what ideal of R, and this is called a product of ideals. Okay, so by this maybe I will stop today's class, and next lecture we will learn something new.